Hello and welcome to EUMETSAT. My name is Mark Higgins. In this series of videos we're going to be walking through how you can discover, download, manipulate and visualize some of the amazing Copernicus Sentinel-3 data that we provide. In the following videos we're going to introduce you to some of the EUMETSAT product experts. They're going to walk you through how you use some of the free and open tools like BRAT, SNAP and QGIS to really get under the skin of these data, to manipulate it and visualize it. We really hope that you will enjoy and use this data in your work or your curiosity about the Earth and marine environment.
Welcome to EUMETSAT. My name is Daniel Lee. I work here as a software and data format engineer, and we are standing in front of the Copernicus control room where some very exciting things are happening. They are processing and controlling data from the Copernicus satellites, which is coming down from space. And exactly that data is going to be the topic of this video. We'll be accessing that data and looking at how you can visualize and process it, as well as data which has been produced on the basis of the observations of these satellites. The topic of today's video is data which is stored in the NetCDF format. This is a very common scientific data format, and it's widely used in the scientific community, in the various scientific communities, because it's very flexible and expressive. You can imagine it's like HTML. You can use HTML to express any web page that you like, and NetCDF can be used to describe any scientific data. This also means that it's hard to make a program that can interpret any NetCDF file, and so for this reason, all of the Copernicus data that I'll be showing to today, and in fact all Copernicus data in general, adheres to certain conventions which tell users and also software specific places that they can look within the file in order to discover what data is there, what it's all about, etc. The conventions that are really important are the ACDD, which is the Attribute Convention for Data Discovery. This helps you find data. And the Climate and Forecast Conventions, which are also known as the CF conventions. And these together make it very easy to discover and also process data formatted in NetCDF. Today we'll also be making use of several software tools. There is the GDAL library, which is the Geospatial Data Abstraction Library, which we will use to process geospatial data. The NetCDF tools, we'll be using the Panoply visualization tool from NASA. We'll also be using QGIS. This is a package for visualizing and processing geospatial data. And we'll be using several Python packages inside of a Jupyter notebook, most specifically the SciPy stack, including NumPy and Matplotlib, Xarray for processing NetCDF data, and the SciTools for plotting this data in a geospatial context. And all of these resources are linked in the text below the video. We'll be working today with data from 3 different Copernicus services. The first one is CMIMS, the Copernicus Marine Environment Monitoring Service. This is a service which is focused on monitoring the health of our oceans and providing information which is useful to anybody who has anything to do with the ocean. So these might be fishermen or people who are involved in maritime shipping, but in fact it could also be just normal people like you or me. The second portal that we'll be accessing data from is the Copernicus Open Data Access Portal. This is hosted at EUMETSAT, and it provides access to satellite data as well as level 2 products. These are on the same viewing geometry as the satellite sees when it's flying over the Earth, but rather than recording what the satellite actually saw, which is light and various wavelengths or irradiation, it's geophysical variables which have been derived from what the satellite viewed. The third portal that we're accessing data from is the Copernicus Atmosphere Monitoring Service, also known as CAMS. And CAMS is a great portal to find information about the quality of the Earth's atmosphere. The data here is mostly forecasts and analyses related to the atmosphere's composition and various variables which help us to understand what's going on there. If you would like to know more about these different portals and the services themselves, let us know in the comments. For the focus of this video, we will be looking at the NetCDF data, which I've already pulled down from these portals, and I'm going to show to you with the software tools which I mentioned before. The first tool I'd like to show you today is Panoply. It's a tool which is designed to allow us to open NetCDF files, inspect their contents, and visualize them, especially if they are geophysical scientific data, on a plot or as various diagrams. And for that I've downloaded some data from CMIMS. Let's take a look at it. The data is stored on my hard drive already, and as you can see, it's a file with a long file name and a .nc file ending, and this tells me that it's a NetCDF file. Because Panoply is already installed on my computer, all I need to do is open it. And if I were to open Panoply directly, I could choose a file that I want to work with. In this case, I opened Panoply with the file in question already, and so it's already open as soon as Panoply starts. On the left-hand side of my screen, you can see the contents of the file. And something that you'll notice about these file contents is that they're structured kind of like a folder which contains files. We have the file name at the very top, and then there are variables below there which are contained within the file. So what the file has is multiple variables all stored in a way that's related to each other, and they might be sharing things such as the location on the Earth or the time for which they're valid. And there are 4 variables within this file: temperature, eastward velocity, northward velocity, and the sea surface height. What we can also see is on the right-hand pane, these are metadata about the file itself. And so if we scroll all the way to the bottom in the right-hand pane, we can see so-called global file attributes. This section contains attributes which apply to the entire data set. For example, here we have the title of the data set, hourly mean fields from global ocean physics analysis and forecast, updated daily. We can find out who produced the data, where to find them on the web, what conventions they adhere to, as well as some information about what time this data refers to and where it refers to above the Earth's center and on the Earth's surface horizontally. If we want to see the metadata for the individual variables, that's also available in the same view. We scroll to the top for that. What's also interesting though, if you don't want to look at all of that data at once, is to just click on a single variable in the left-hand pane, and that limits the display to only the metadata that's related to that variable. So for example, if I click on ZOS, which is the sea surface height, then I can see that that is stored with certain dimensions, certain coordinates, and I can also find out the meters and any kind of scaling and offset values which are relevant for viewing this data set. So now that I've chosen the sea surface height variable, I'm going to create a plot of that. And if I click the Create Plot button, a window opens which asks me what type of plot I'd like. The plot that's most interesting to me right now is the longitude-latitude plot, because that displays the variable on the Earth's surface as a map, which is what we're used to viewing. So when I click Create, in the background the plot is created. And here we can see a beautiful plot of the sea surface height. And something that's very interesting about Panoply is that the data is already labeled. So Panoply not only can understand NetCDF, it can understand specifically geospatial scientific data in NetCDF. And for that reason, it's interpreted what is in this plot, which is the sea surface height. It's applied a color map, which is roughly appropriate for this type of variable. And it's labeled it as well as the units and provided some basic data about the distribution of the variable that we're looking at. What it also gives us is an array of tabs down at the bottom that we can use to customize this map for ourselves. So for example, I might navigate to the labels and say for a subtitle of this map, CMIMS data, and I might also change the map scale or the projection of the map that I want to use. And there are various other things that I can add to this map, including country borders, rivers, etc. So Panoply is really great for getting a first look at your data because it understands your data and can show it to you in a way that you as a scientist or researcher are familiar with. What it cannot do, however, is display multiple data sets together. So if I want to compare the sea surface height with the sea temperature, for example, I can't do that in the same map. Let's take a look at what that would look like. So if I choose the temperature and create a plot of that, I can create a new plot which I can display next to the old plot. But I can't combine them. So while this might be useful for getting a first feel for your data, it's definitely not enough to analyze it numerically and find relationships between the data that you could use in your work or publish in a report. For that, we'll need to use another tool. QGIS is a program which is designed for generic processing of geospatial data. It's not designed specifically for scientific data, but it can work fine with scientific data. It may be in some cases that you have to do a little bit of work to prepare the data so that QGIS can understand it, which is not the case for Panoply because Panoply is designed specifically for that data. Back to the example of combining sea surface height and sea surface temperature. We can do that in QGIS quite easily. I'm going to open my CMIMS folder, and here we'll see I have the same file, and it's represented to me in the same way, hierarchically. So I have the file name and the various variables which are stored in there. And if I double click on sea surface height, the first thing I'm presented with is a question. Which coordinate reference system should I use to interpret this data? The reason I'm asked this question is because the CF conventions, to which our scientific data adhere, don't present the coordinate reference system to QGIS in a way that it understands. There are many types of coordinate reference systems, and they determine how to interpret coordinates which are associated with data. For some local maps, you might have coordinates which are in meters, or even in feet, or miles, or kilometers. And this is not often the case for global data. Global data normally uses latitude and longitude to record the position of an item on the Earth's surface. Because I know that's the case for this data, and also because it's a safe assumption for global data, I'm going to choose the classic global projection for my data, which is WGS 84. This is the data which is used most often for data which applies to the entire globe. So if I click OK, the display that pops up is now a map of the Earth, it seems. I recognize that it's a map of the Earth because I can see the continents basically punched out of the outline of what is the sea surface temperature. And this looks like it's in the correct position. I can also add on top of that the temperature, which I'm doing via the same dialog. And when I do that, that's also added to the map. And I can toggle back and forth between them so you can see that they are indeed different maps. They do indeed lie on top of each other. And if I want to really verify in a quick and easy way that the maps are positioned correctly, I can add some more data from another data set. And in order to do that, I'm going to pull in some polygons which represent the land coverage of the Earth. This is a free data set from Natural Earth, and it's simply a map of the continents. And when I add that to the map, you can see immediately the continents lay where we have holes in our ocean data, which makes perfect sense because continents are in places where there's no ocean. They all lie perfectly on top of each other, so it looks like we've successfully combined 3 data sets from 2 different disciplines. And in this case, we might continue to work with them. That's great. What we've just done is visualize 3 different data sets from 2 different data sources all together, and we can see that in QGIS they're all lying on top of each other. Now, just as a quick note, QGIS has a lot of options to further process raster and polygon data, or any generalized vector data. For example, we could do silly things like add together the sea surface height and the sea surface temperature. In a more relevant sense, we could take the eastward and northward velocity data sets and use them to compute the actual wind vectors and the wind speeds. So these are things that are all possible within QGIS, and because it has so many options, it's way beyond the scope of this video. But what I would like to show is a way to set a different color map, because that makes the data a lot more attractive. For any given data set, and these in particular are raster data, you can access the display options by a simple double click. What I have here is the symbology tab for the sea surface temperature. And it's only one band of data, and currently it's displayed in grayscale. But if I select single band pseudo color, then I have an array of different color scales which I can select and customize. I'm not going to change this right now, but I'll use just a basic different color layer, and what you can immediately see is that the data looks different. And for people who really work with colors a lot, you might be able to recognize more detail, more features within this data. So that's really good. Now, what happens if we want to add additional data? I'm going to now add to the map some data from the CODA portal. So if I want to add some CODA data, which is stored again in the satellite viewing geometry, to this map, it might be a straightforward process. So now I'm going to select the CODA data on my hard drive, and I see again a NetCDF file and it's stored with a number of different variables. This is more complex data. And for the sake of simplicity, I'm going to choose the sea surface temperature variable from this because it combines well with the data that I already have on here. So if I double click on the sea surface temperature, I'm again asked what coordinate reference system should be used to interpret this data. And if I apply the global coordinate reference system, WGS 84, which I had done for the previous data, it looks rather confusing at first glance. In fact, we see almost nothing except for this little bit off in the corner. And if we right-click on the data set and select Zoom to Layer, you'll notice that the layer is actually off somewhere in an impossible position. It's below the South Pole, and that just doesn't work. Now, I'm showing to you this mistake because it might happen to you, and I want you to be able to find out why this is happening. So let's do some data archaeology. I'm looking at the data, and I know because I selected the data previously that this should be displaying a region over the Mediterranean Ocean, and I should be able to see some of Italy and some of Greece. And looking at the data, I see if I mirror it on two axes, so north becomes south and west becomes east, that looks a lot like Italy, and that looks a lot like Greece. So this is the first thing that's suspicious to me. The second thing that's suspicious to me is if I move my mouse around the map, I can see down here the coordinates that my mouse is over. And these coordinates, if I go to the top left corner, which is located on the Earth, seem to begin at 0, 0 degrees. Now, because we're looking at local data that is stored the same way as the satellite saw it, it wouldn't make sense for these to be stored as decimal degrees like the other data is. But it is telling that 0, 0 maps to a place on the Earth. And the reason that there's no data displayed there is probably because that position within our data isn't actually over the ocean, whereas the data only contains information about the ocean. There's some more archaeology that we can do from the terminal command line. So now I've opened a terminal, and I'm going to navigate to the CODA folder. And if I view the contents of the folder, I see the NetCDF files contained there. And I'm going to use GDAL, which is the Geospatial Data Abstraction Library, to display some data about this. GDAL info is a good tool to just dump some basic info about what a file contains. And if I execute that on the file, I will see at the very bottom of the exhaustive information that it outputs something impossible. The corner coordinates, which bound the data, go to 512 degrees, and 512 degrees can't exist on the Earth. So something definitely is wrong here. If I open the same data set in Panoply, just to make sure that the data is not corrupted in some way, what I will see is that Panoply is able to display it just fine. That tells me that I can trust the data much more than I might have thought initially. Now I've opened the data in Panoply, and I see roughly the same as I saw before. And I'm going to create a plot of the sea surface temperature, which is the variable that I opened in QGIS just a few minutes ago. When I do that, the plot opens, and luckily the data isn't located somewhere far away from Earth in an impossible place. Instead, it is located where I thought it should be, as you can see on the map. I'm going to change the map now so that we can see it a bit better by zooming in on it. And for that, I'm going to use a different projection. So I'm going to take the coordinates that I have, which might be global, and transform them into another coordinate system so that we can see them better. And so now I'm zooming through all of the available projections that Panoply has to offer. And as you can see, it's quite a few. If I select transverse Mercator, then the map doesn't look quite as descriptive as before. The reason for this is that transverse Mercator is a projection for local data, which fits well to our data, but it's not positioned at the correct place right now. I'm moving the center of the map now to 20 degrees east and 36 degrees north. And when the map updates, you can see that there's our data and it's in the correct position, which means that somehow Panoply can interpret the data, whereas QGIS cannot. How is it doing that? We can find out some more information by using the NC dump tool, which is a tool for viewing the contents of a NetCDF file. if I execute ntdump on the file that I'm interested in, it will give me all of the data which is contained in the file, and that's quite a bit. So I'm going to use the -h flag, and I'm going to pipe the output to the program less, which will allow us to scroll through that data. Now I can see the contents of the data as text, and if I search for sea surface temperature, I jump to the variable in question, and I can see a lot of metadata which is associated with it. This, by the way, is the same view which is presented to you in Panoply. And we can see that sea surface temperature has a couple of interesting things for us. It has an add offset, which we'll need to interpret the data later on. It has a scale factor, and it also has coordinates, which are lon and lat. So what it's referring to with the coordinates are actually other variables contained within the data, and what they have is the actual coordinates where the data is located on the Earth's surface. What we were looking at in QGIS were the coordinates within the array of data stored on the hard drive. Of course, for me as a scientist, I'm much more interested in where my data comes from on the Earth than where my data comes from on my hard drive. So let's go back and use GDAL to extract those coordinates and apply them to the data now. The tool to do that with is GDAL warp. So I'm going to run GDAL warp. I'm going to use the parameter geolock. Geolock means extract geolocation information. And now I need to tell GDAL warp what data to interpret and how. So I'm going to say this is a NetCDF file. I provide the name of the NetCDF file, and I also provide the variable that I'm interested in, which is sea surface temperature. And now I need to provide an output file name. And I'm going to call this SST for sea surface temperature.tiff to produce a geotiff file. When I hit enter, GDAL processes the data and gives us a bit of output so that we can track it, and now it's done. If we return to QGIS, we'll be able to see that output now. I'm now removing the sea surface temperature layer from my map because it's not useful the way it's loaded in there. By selecting remove layer, QGIS asks me to confirm that, and now when I scroll down within my folder, I can see that that new data set is available, sst.tiff. Double-clicking that asks me again, what coordinate reference system should I use? And when I click OK, using WGS84, I don't see something which is located far away from the Earth. Instead, I see a little tiny fleck of color, which is in the Mediterranean Ocean. Let's zoom into that. Right-click on the data set. I select the option Zoom to Layer, and when the map updates, I can see that the data is indeed located where I expect it to be, and it looks good. Now, something that should be noted here, if you're looking at the map legend, you'll see that the data spans the domain from -299 to +4420, which doesn't make sense. We know from looking at the data that it's stored in kelvins. Those would not be possible temperatures to find in the ocean on Earth. In fact, anywhere. And the reason for this is because of the aforementioned scale factor and add offset. If we want to interpret this data, we need to apply those two factors in order to unpack the data and show it in its native units. And if I were to do that, the most likely choice that I would take would be to use the map calculator, which is available in QGIS, but which is outside the scope of this video. What we've just seen is QGIS and its power for combining multiple data sets from different disciplines and showing them together, and also possibly for processing them to make great maps or to make great data. QGIS is very, very powerful if you're willing to sit in front of your computer and click something together. It's very interactive, it's easily approachable, but sometimes you have a workflow that you've already defined, you know how it works, and you want to program it so that you can be producing data on a daily or an hourly or a minutely basis. And for that, QGIS isn't the best platform. Instead, I'm going to show you an example of how to do something similar to that in Python. And this can be executed completely without human interaction. The environment that I'll be using for this is a Python notebook, because notebooks are good ways to produce reproducible research. If I give you a notebook, what it contains is an explanation of the steps which are going on, and then the actual code which is executed in the course of this research. And what you see in the notebook is not only the code, but also the results. And it's executable on your side as well, which means it's as big of a revolution as if I could give you all of the materials in my lab and the lab itself so that you could reproduce my experiments. Very, very exciting. I have a Jupyter Notebook server running on my computer at this moment, and so all I need to do to interact with it is navigate to it in my web browser. The data that we'll be working with is from the Copernicus Atmosphere Monitoring Service, and what you see on my screen right now is the CAMS portal, which I use to download the data. The data is stored on my hard drive, and I have a Jupyter Notebook which I've prepared for you with explanations and code, and this will be accessing that same data. This notebook is available on the web, so you can download it and play with it yourself, change it to match your needs. Let's get started. This is a notebook that will be executing in Python 3, which is the future of Python, and if you worry about using Python 3, please don't. Python 2 was the main Python version for a long time, but now most libraries, and especially all scientific libraries of relevance, have been ported to be able to work with Python 3. So this really is the way to go. We're going to start by importing all of the tools that we need. And that's this block right here. It just imports NumPy, the PyPlot module of Matplotlib, Xarray, which is used for accessing NetCDF data, and the CRS module of CartoPy. CRS is for Coordinate Reference Systems. NumPy and Matplotlib are both from the SciPy stack of technologies. Xarray is a package which is designed for working with NetCDF data, big arrays, multidimensional data sets, and CartoPy is from the SciTools family of libraries, and it's designed for working with geospatial data in a scientific context, and we're going to use that for mapping. I execute that by hitting Control-Enter, and I'm not expecting to see any output here because all of these libraries are installed on my machine, and so all that's happening is that I'm gaining access to them within the context of this notebook. So now we've imported all of the libraries that we need, and in the next cell we're going to import the data that we want to work with. And we'll be doing that by making a call to the Xarray function OpenDataArray. OpenDataArray is right here, and we pass into this function the file name that we want to gain access to, and that is stored under the folder on my machine, CAMS, and it's a NetCDF file, as you can recognize from the file name. And we assign the result to this variable right here. We're calling it NO2 because this is nitrogen dioxide data. And in the next line, I just spit out a summary of what this NO2 data is so that we can see how the computer is viewing it. Now what we see is the summary of the data that we just loaded. We see that it has 3 dimensions, the latitude, longitude, and time dimension. And we also see the content of the data itself, namely total column nitrogen dioxide with units kilograms per square meter. And that's great. That shows that our data can be understood by Xarray and presented to us. And now I'd like to make some very basic plots with this. So the first thing I'm going to do is make a plot of the total column nitrogen dioxide over a point on the Earth's surface. There are multiple ways to do this. I'm going to show you 2. The first one is to select by index. So what you do is you call the object which we've created, which contains the data. That's the NO2 object. And we're going to call its method iSelect. This stands for index select. And I pass in the indices and the positions within those indices that are interesting for me. Those are latitude and longitude. And I've passed the number 0 to those. That tells Python to pull out the first position within those arrays. So it's going to pull out all the NO2 data that is located at that position and assign it to the variable first point. We could do this, and when I execute the code, it will run without any problems. But it's actually not very interesting for us from a scientific standpoint because, again, the iSelect is using the position within arrays. And as scientists, we're normally interested in the position on the planet Earth. And so in order to select that data, to select according to those criteria, I'm going to use another method. So again, I access the NO2 object. I call the select method, not the iSelect, but the select method. And this will select based on values that I pass into the call. So I say I would like to have all data which is located at the latitude 50 degrees and the longitude 8 degrees. And I'm assigning that to the variable named Darmstadt because that's where I live and work, and so that's interesting for me. And in the next line, one down, I plot that data. Let's execute that now. Now what you see is that the call was executed and a nice plot is produced. It's a line showing the evolution of NO2 values for the total atmospheric column above Darmstadt for the month of June this year. And we can see that the axes are correctly labeled. So at the very top we have the position which this is extracted from, longitude 8, latitude 50. On the y-axis we have the total column nitrogen dioxide, and on the x-axis we have time. And we could recognize a certain cyclical pattern throughout the month, which is interesting. We can also compare two different places on the Earth in the same plot as follows. So I'm doing much the same as I did before. I'm accessing the NO2 object, calling the select method. I pass in the latitude of 50, and instead of passing in a single longitude value, I pass in a list of values, 1 and 8. I've chosen these values because they're approximately the positions of EUMETSAT in Darmstadt and ECMWF in Reading, both of which participate in many of the Copernicus services. And I choose the method nearest. That means that if exactly those coordinates are not contained in my data, X-array will select the nearest available coordinates. So this may not be exactly the position that I specified, but it'll be close enough for our purposes. I could store the result of this call directly in a variable as I did in the previous call, but instead I'm going to use it directly without storing it anywhere. So I call the plot method of that, and I tell the plot method that I want it to create a line plot and that the x-axis should be the time dimension. When I execute that, what we'll see are two lines. The plot is much the same as it was before, but rather than telling me the longitude coordinate at the very top, it tells me the longitude coordinate in the legend with the color which corresponds to it, so that I can find that in the plot. And what I can see here is that I have two different color lines. One color corresponds to Darmstadt, the other corresponds to Reading, and it looks like in the month of June this year, Reading had less nitrogen dioxide in its atmosphere than Darmstadt did. What if we want to get a feel for the data? Well, there are lots of different things that we can do because now the data is available to us in Python, so we can apply the full array of Python libraries to process it, and that includes a lot of scientific software that we can access and use right away without needing to write it ourselves. So I'm going to show you a contrived example. It doesn't make much sense for many applications, but it shows the power of what we've done here. I'm going to call the NumPy library, and from that library I'm accessing the log function. This computes the logarithm of an array of data that I pass into it. I pass into it our NO2 data set and ask NumPy to make a plot of that. And here we see the plot. The plot is a histogram of the logarithm of all of the NO2 data that is stored in our data set. So in this one line of code, we've iterated over all of the data stored there for all time steps, for all positions on the planet, and have computed the logarithm, and then we made a histogram of all that. That's very exciting if you're a data researcher. But what if you want to see the data on a map? If you're interested in the spatial relationships between the data, we can create a map of that, also within Python, and display that in this notebook. So what I've done here is I've accessed the NO2 object, and I'm going to use the iSelect method. This is selecting by index, as we said before. And I'm selecting by position within the time index. That's why this argument is set to time equals 0. So it's pulling out the first time step in the data for all locations on the Earth. And I'm doing this because oftentimes you're interested in the oldest data or the newest data in your time series. I create a plot of that, and that's actually enough to create a map of that time step of the variable I'm looking at. But in order to make that map easier to understand, I've passed an additional argument into it, which is robust equals true. What does this do? It removes outliers from the creation of the color map. And this will allow us to see some more detail, because outliers can have a big impact on where the color map is stretched to. I'm removing them so that we can recognize more in our map. So now that I execute this line of code, you can see a very, very basic map of the Earth. So we see the total column nitrogen dioxide with a legend on the right side. On the left-hand side, the y-axis is labeled as latitude, and the bottom, the x-axis, is labeled as longitude, and we see what time specifically comes into question here. And that's also interpreted in a way that we can understand. This makes a kind of strange map because the 0 coordinate is 0 degrees east, which lies over England. So that means that on the left side we have the very edge of Europe, and on the very right side we have again the edge of Europe, and the map is centered over the Pacific Ocean, which is fine if you're an oceanographer or if that's your point of interest. But it's not the map that most people will be used to dealing with. That doesn't bother us right now. What we can see is that over Asia and Australia, and also over the Americas, there seems to be some higher concentration of NO2 over areas which are heavily settled by humans, which matches everything that we know about SO2's development in the atmosphere. So that's great for getting a first look at this global data on a map. Now, I'm from EUMETSAT, and I'm interested in satellites. So what I'd like to do in the next step is to look at the data much as it might be seen by a satellite. So I'm going to create a new projection of the Earth, which will seem as if we're looking down at the Earth from above. I'm going to do this using matplotlib. So that's in this cell right here. I call matplotlib, and from matplotlib I call the axes function, and I pass in as an argument that I'd like to use a specific projection. What projection do I want to use? I want to use a projection from the SciTools family of libraries. This is from Cartopy, and it's the orthographic projection, which just means it's the projection as if I were looking at the Earth from above. And I want to center this map at 8.7 degrees and 49.9 degrees north. This is roughly the position of Darmstadt, so again, we'll be looking at ourselves from above, so to say. We take the result and we assign it to the variable ax. This is shorthand for axes. And in the next line, we call the coastlines method of this object to add coastlines to it. This will give us a better feel for what we're looking at. Now in the last step, we're going to add the data from our data set to these axes, so to the plot. And we do that by calling our NO2 data set and using the iSelect method. And now we're going to select the last item according to our time dimension. So this is the most recent data which is stored in this data set. We call the plot function of the result, and in the plot function we do two things. First, we transform the data onto another projection of the Earth, namely to the plate carré projection, because many people are used to looking at the Earth this way. And secondly, we do the same thing as we did before. We set robust to true to remove outliers, and this will help us to recognize details and features in our data. I just executed that code, and if I scroll down, what I see is a map of the Earth. Everything is transformed correctly to be round and on a globe, and it is the correct time point, it's labeled correctly with a legend, so that's great. Now one last thing I'd like to show, and this is something about the power of working with Python and working with notebooks, is that I can go back to any point in this file and change things and re-execute the whole thing. So in this example, I'm going to set the orthographic view to 0, 0, which is the same view as our Meteosat satellites see. So they're centered over the prime meridian and the equator. I set that to 0, 0, but I could just as well change something at the very beginning of the script. For example, I might change which data set is read, and that would change what's plotted. Nothing else, no other further work would be required in order to completely change what I've done. And now, if I go back to the beginning and say, run all cells, for example, all of the cells are executed, and you can see the results are the same as before as they pop up. And you can also see that the final view which is produced is different. This is the view that we see from Meteosat. As a researcher, that is huge because it often happens that you have something that you need to change in your workflow, and this prevents you from having to repeat every subsequent step. You just change it in the script, re-execute, and you're fine. This is great for producing reproducible research, and it's also great for prototyping workflows that you might want to apply in production. So that's it for now. What we've seen today is visualizing data from the Copernicus Atmosphere Monitoring Service, CAMS, the Copernicus Open Data Access, CODA, and the Copernicus Marine Environment Monitoring Service, CMIMS. And we've learned to use several tools to visualize and analyze our data. Panoply for basic visualization, GDAL and NCDump, and the NC tools in general for diagnosing issues with our data, QGIS for combining data sets, and finally several Python libraries embedded in the context of a Jupyter notebook. I hope you're as excited as I am to work with the Copernicus data and that this video has been helpful for you in your work. Keep an eye on our channel for further educational videos, and see you soon.